Good evening. Good evening. Anyway, hello. This is my Matlab project for numerical methods. This is a root finding tool tutorial in this project where we will explore multiple numerical methods to find roots of function. So as you can see, we will run main here, and you will find in the command window that there is an enter function. So let's try tangent of x minus 1. And the start of interval will be 0, and the end of the interval would be 4. Now we will first choose the incremental search. Executing. As you can see, we have the root over here between 0.5 and 1. And that's it. And next, we will try Newton-Raphson method. So let's see. Let's try sin x minus 0.3, and let's have the start of the interval be 0 and 10 will be the end of the interval. Okay, let's choose Newton-Raphson method number 5. As you can see, it has multiple roots. And next, we will try secant method. We have tangent of x minus 2. We'll have the start at 0 and the end of the interval at 7. So let's choose number 6, secant method. Okay, and as you can see, we still have multiple roots. This is the table. By the way, I'm sorry, I forgot to show. As you can see, that's a lot of iteration. Next, we will try bisection method. We have sine x minus 0.5. We will have the start of the interval. Since it's this equation, we will assume that the start will be 0.4 and the end will be 0.7. So let's choose bisection method, which is number 3. So the step size, you can have 0.001, or if you want much more very precise assumptions for the root, then you can go smaller with the decimal places. But let's try 0.001. And the tolerance would be 0.001 still. 50 max iterations. You can see here's the root between 0.5 and 0.55. The root is 0.5230. Next, we will try, we will try postposition or regular falsy. We have cosine of x minus 0.7. Since this is the equation, let's assume that the start of the interval will be 0.5 and the end would be 1.5. So regular falsy number 4. So you can see here's the root between 0.7 and 0.8, which is very close to it. That's there at the boundary. So the root is 0.795397. And last but not the least, let's try how about we try graphical method. There's graphical method. We had the same result as the bisection method we have, which is 2.6 between 2.6 and 2.7, and here's the root. And that's all for the running of our Matlab project. This is the source code. We have here the inputs needed for each method. And also here we have the necessary things needed to actually solve the functions, the requirements, and the we also have the statements needed to actually that statements needed to actually be able to solve the function or equation that our users will give. Same with the incremental method. So first, the graphical method. It's a visual approach that estimates root by plotting the function over an interval. You see here, it's plotting over an interval, and then identifying where it crosses the x-axis, because as you can see, the graphical method runs works just like a graph. So this is a simple but effective way to get the initial root estimates, especially useful when you don't want to perform heavy calculations. So basically, this is the most basic method that you will learn in the numerical methods. Next is the incremental source code, where you can see here it scans the function value step by step across the interval to detect sign changes. So when you detect sign changes, that would indicate that you have found the root, that you have found the root. Basically, that's just how it works. Next is the regular fallacy, which is similar to the principle in bisection, which I am about to introduce. So this instead of taking the midpoint, though in bisection, it uses a linear interpolation between the interval and points to guess the root. This often leads to faster conversion than bisection. So if you want to talk about bisection, the bisection method is still a classic root finding algorithm based on still repeating intervals. So it requires an interval where, let's see. So it requires an interval where the function changes sign. That is, the function values at the ends of the interval to have opposite signs. So this method basically repeatedly narrows down this interval by computing the midpoint and determining which half contains the root based on the sign of the function. So next is Newton-Raphson method. So it is still an efficient root finding algorithm that uses the function derivative to find successively better approximation of the root. So you can see it's still plotting and so on. So in our project, if the user selects Newton-Raphson, the derivative is either calculated symbolically or entered manually. So basically starting from initial guess, the method, let's see, initial guess. So you can see this is the input text. So the method applies the formula x new equals x old minus f of the function of the old x divided by f prime of derivative of the old x. So last but not the least, oh my god, is the second method. So this is similar to Newton-Raphson as I have mentioned earlier. But this does not require the derivative, as I have mentioned, because it approximates the derivative by using two recent points to form a secant line and calculates the next estimate accordingly. It uses two initial guesses. As you can see, let's go find the prompt that asks the user for two initial guesses. So then after that, it iteratively computes root approximation, stopping when the desired tolerance is met or maximum iterations is reached. So that's how our code scans the interval, applying the second method for overlapping pairs, outputs iteration details, and plots the roots. That's all. Thank you.